Hello everyone and welcome to Physics Lab. So this video lecture is for Lab 0, which is just going to be on graphing. I want to make sure that everyone is comfortable using the Pasco Capstone graphing software. So this is software that you can download, you can put on your own laptop, and there's a license there that you can use, and then you can use the software whenever you need to use it. You can have it forever. So basically, the link to the website to download it, and that link to the license code is going to be on Brightspace. So if you check out Brightspace, you have all those links for Pasco Capstone. Okay, so this first lab, it's very similar for all three of the labs I teach, for Physics 206, which is Sports Physics Lab, Physics 207, Physics and Movement Science Lab, and Physics 212, which is a General Physics Lab. So this video will be fine for all three labs. The only difference is one part, and I'll let you guys know when it occurs, that Physics 206 does not have to do. Okay, again, I'll let you guys know that when we get to that part. All right, so to begin, let me bring up the handout on measurement. So if you guys can look at your handout on measurement, where we have a poorly drawn graph. We'll start with that first one. Okay, so if we look at this graph, this is an example of a poorly drawn graph, right? There's some issues with this graph. So the first thing is you want to make sure that you have good labels. So here on the y-axis, I have A, and on the x-axis, I have F. But what does that mean, right? A better label might be, let's say this means acceleration. So maybe acceleration and then versus force, right? So good labels. Now, along with labels, you want to make sure you have units, right? So acceleration would have to have units. Let's say it's, you know, meters per second squared, and force would be, say, in newtons. Okay, so labels with units, very important. You also want to make sure you have a title to your graph. So an easy title to give, if you can't think of a good name, is always give the dependent variable, which is the y variable, so in this case it'd be acceleration, versus the independent variable, which is the x variable, in this case force. So if you just call this graph acceleration versus force, that would be fine. Okay, so always y versus x, or dependent variable versus independent variable for the title. Okay, another thing, typically we want to represent, like this graph should represent the relationship between these two variables, right? So we want to represent the relationship between, let's say, acceleration and force. Now, this may not be the best way to do it, just by connecting our data points with line segments, right? Probably don't want to do it that way. It doesn't really show a relationship. What you want to do is you want to have a curve of best fit that goes through all of your data. In this case, probably a line of best fit would be best, right? So if we have a line that fits the data the best, that would be the way that you want to do it. Now, the last point is very subtle. So the blue points right here are data, right? And they come from, you know, collecting maybe several trials and averaging them. And typically there's some error in these data here. Now, if you look at, you know, say a journal article, sometimes what they'll do is they'll represent the error by using like error bars. So usually there's some like indication of the error in your data. Or you could even just qualitatively represent the fact that there's error by circling your data points, okay? So you want to represent the fact that there's some error with your data. Now, again, you guys don't have to worry about this too much. I'm not going to have you circle your data point or calculate error bars or things like that. We will calculate something called percent experimental accuracy in lab 1, but you don't have to represent that on the graph. But typically it is done, so I just wanted you to be aware of it. Okay, so let's look at the second page on this handout. This is a graph that's drawn much better, right? So it has labels, In this case, I have range plotted on the y-axis, and it has units of centimeters, and I have angle plotted on the x-axis, and its units are degrees. So I could, for the title, I could say range versus angle, which is sort of what I did here, added a little bit to it, but same thing, right? Range of a projectile versus angle of projection. You could just say range versus angle, and that would be fine. And then, again, in this case, you guys don't have to do this, but I circled all the data points just to show that qualitatively there is some error in those data points. And then I did a curve of best fit, which happens to be a sine wave in this particular example. So that red line is my curve of best fit. Usually in our lab, your curve of best fit will be like a linear fit often, maybe a quadratic fit. We'll see later in this lab that we're gonna have to do a power fit for one of our graphs, but typically it's like linear, quadratic, those types of fits. Okay, on the third page, this is just an example of how to calculate the slope of the line of best fit. Now, again, in lab, for you guys, it's not going to be such a huge deal because when you do the fit, the computer program will calculate the slope and it'll give you that information. It'll give you the slope of the line of best fit. But let's say we wanted to do to calculate a slope by hand, right? So in this example, I have velocity plotted on the y-axis in meters per second. I have time plotted on the x-axis. So the blue points are my data. And it looks linear, so I do a line of best fit. And now I want to calculate the slope of that line. So here's the thing that you don't want to do. You don't want to just choose two of your original data points and calculate the slope between those 2 points, right? What you really want to do is you want to choose 2 points on the line of best fit. So you want to do the line of best fit first, choose 2 points on the line of best fit, and then calculate the slope. So in this example, I chose this point right here. So the time is 5 seconds. The velocity was 14, right, meters per second. Then I chose this point. So the time is 15 seconds, and then the velocity looks like 34 meters per second. So now to calculate the slope, remember the formula is, usually we say y2 minus y1, but in this case, since the y variable is velocity, you can think of this as v2 minus v1, so it'd be 34 minus 14, which is 20, so the change in velocity, or v2 minus v1 is 20. And then we say over x2 minus x1, but x variable is time, so you can think of it as like t2 minus t1. So 15 minus 5 is 10, so my change in time is 10. So therefore, to calculate the slope, it's going to be the change in velocity divided by the change in time, right? The rise over the run. So 20 divided by 10 would be 2, and then the units would be meters per second over seconds per second. So it'd be meters per second squared. And it turns out, and you guys will learn this later, you don't have to know this right now, but it turns out that that slope of the velocity versus time graph represents the acceleration. In this case, it's pretty much constant acceleration of 2 meters per second squared, okay? But again, the point I wanted to make was that when you're calculating the slope, make sure you use 2 points on the line of best fit. Okay, don't use 2 of your original data points. Okay, so the next page, so this is the part where this is going to be really important for Physics 207 and 212. Physics 206, you don't have to worry about the pendulum part, so you can skip this part. Okay, so if you're in 206, you can skip this part, but you should pick up a little bit later, all right? Just skip this one part on the pendulum. For those of you who are in Physics 207 and 212, one of the things we want to do in this lab is we want to look at the relationship between the period and length of a simple pendulum. Okay, so what is a simple pendulum? And I'll actually show you guys a simulation in a minute. So think of a simple pendulum as consisting of a string or a lightweight rod, where at the end of it you have a mass. So the mass is focused at the end. Then you displace it, let's say to one side by some small angle, and you release it, and it's going to oscillate back and forth. Okay. Now the time for one oscillation, that's going to be the period of that simple pendulum. So we want to look at the relationship between the period and the length. So when we change the length, how does that affect the period? All right, let me show you what this looks like in terms of the simulation. Okay, so here's the simulation we're going to use. So again, you can think of it as, let me pause this. This black line here represents the string, right, or the rod. Here's the pivot point. This is the mass. The blue object is the mass of the pendulum. We're going to displace it by a small angle, maybe 20 degrees. So I'll just go to -20. Negative, by the way, means clockwise and positive is counterclockwise. So negative just means I'm going to the left, so it's clockwise. And then when I press play, that pendulum is going to oscillate back and forth. So the time it takes to go from there back to there is the period. So one oscillation, time for one complete oscillation would be the period. And then to change the length of this, what we can do is up here on the slider where it says length, I can move this. So if I go all the way down, that's 0.1, this is in meters, but 0.1 meters is the same as 10 centimeters. And I can go up from there. Actually, if I just move the slider here, it goes up by 0.2 meters at a time. And notice that the period changes when the length changes, right? So when the length is shorter, the period is smaller, right? It's faster, it's oscillating back and forth more quickly. So again, our goal is to look at the relationship between the period and the length of that pendulum. Okay, so here's something that's really interesting. If I do a graph and I plot period squared, so if I square my period values and plot them on the y-axis versus length on the x-axis, it turns out that the relationship is linear, right? So here's my data points, and I can do a line of best fit through those data points. So one of the questions that I'm going to ask you guys to answer in the lab report is I want you to come up with an equation that gives the period as a function of the length. So the period as a function of the length. And we're going to use this idea from this graph to help us come up with that equation. And I'll help you guys out with this. So again, if I plot period squared on the y versus length on the x, I get a linear relationship, right? A linear fit here. So how does that help me? Well, let me go to the iPad to show you this. Okay, so think about the equation of a line. And there's many ways that we can write the equation of a line. There's different forms, like the standard form. Probably the one that you guys are most familiar with is the slope-intercept form, right? So remember, one way of writing the equation of a line is we can say y equals mx plus b. And remember, in this example, what is our y variable? In other words, what's plotted on the y-axis? It's period squared, right? Period we usually represent by capital T, kind of means like time, right? So I'm going to call the period t, but my y variable is actually t squared. That's got to equal the slope m times the x variable, but what was plotted on the x-axis of that graph? Remember, it was the length, right, of that pendulum. So I'll call that, say, L. And the only other thing we need is the B. So the B would be the y-intercept, right? But in that particular graph, you go back to that page, and we'll go back to it in a second. It basically passes right through the origin, right? The graph goes to the origin. So that means that the y-intercept will be 0. And we're going to assume it's 0 in this case. So I'm just going to assume b is equal to 0. Okay, so this is great. This is a good start. We have period squared equals m, the slope, times the length, times L. But remember, what we want for the final equation is not period squared, but the period as a function of the length. So mathematically, how do I get the period if I have period squared? I can simply take the square root, right? It'll undo the square. So I'm going to take the square root of both sides. If you're being really careful, remember when you take the square root, it's going to be plus or minus. But in this case, we don't want negative periods. Doesn't make sense to have negative. So I'm just going to take the positive root. So this is going to be plus. So square root of t squared is t. So that's my period. And that's going to equal the square root of m times the square root of L. But I can break that up, right? Using radicals, I could also write this just as the square root of m times the square root of L. Okay, great. But we know what m is. Remember, m is the slope of the period squared versus length graph, right? So we can figure that out. When you guys do this graph and you do your linear fit, you will have that slope value. So you can plug in for the m here. We can find this value for m. We can plug in for m. The other two are just variables. They're going to stay variables, the t and l, but we can figure out what m is. So actually, if I go back to the handout, we can look at that. Okay, so in this case, we have period square versus length. Right? So this is my linear fit. So I would choose 2 points in a line of best fit. Right? Assume I did this by hand, right? And you guys do it on a computer, it'll give you the slope value. But in this case, I chose these 2 points right here. So now to calculate the slope, I need the change in the period squared. It's like my y variable. So change in period squared is going to be 0.8, right? 1.6 minus 0.8 is 0.8 over the change in the length. So I have 40 minus 20, which is 20. And then if I divide now, 0.8 divided by 20, so rise over run, that's going to be my slope. And if you work that out, you're going to get 0.04. And it turns out the units are seconds squared, right, for period squared over centimeters to the length. So 0.04 is my slope. Okay, so where I have m now, I can plug in 0.04. So you can simplify that, right? Square root of 0.04, just do that in your calculator. It turns out it's 0.2. And then times the square root of L. So, and this is exactly what I wanted, right? This gives me the period t as a function of the length L. So that was the equation I was looking for. So you guys will have, for that answer, you will have a very similar equation to this. The only thing that's going to differ is you're going to use your particular slope value, m here. So you might have a slightly different number there. It'll probably be close to 0.2, but you might have a slightly different number depending on your values that you get when you do this part of the experiment. Now, what does this look like? Well, if we were to plot this, so let's say this is length in centimeters, and then period in seconds. If I plot this square root function, it's sort of like a sideways parabola. So it looks kind of like that when you plot it. Okay, and again, I'll show you guys this when we talk about the graph for this particular part where I do period versus length. but it should look like a sideways parabola. All right, great. Okay, so bring up your lab handout. Let's talk about the lab handout for this first lab. Again, it'll be very similar for Physics 206, 207, and 212. The only difference is Physics 206 will not be doing the pendulum part. Okay, so the first part, part A, basically I just made up some data that represents a cart that's moving on a horizontal air track with no friction. And the first column represents the time in seconds. And the second column represents the position in centimeters of that cart. So what we want to do, and this is question 1, is we want to plot a graph of position versus time, which means time is going to be on the x-axis. You might want to make a little x here to remind yourself of that. And position will be on the y. So maybe we make a little y there to remind yourself position is y. So then based on the shape of your graph, what type of curve, right, would you fit to your data? Perform the fit. What is the slope of your graph? Now, by me asking for the slope, I'm kind of giving you the previous answer. Like, what type of graph has a constant slope? It's just one particular slope. It would be a linear fit, right? So it's going to be a linear fit for the first part. And then you want to record the value of the slope in the table here below. Now, I created a second video explaining how to use Pascal Capstone for graphing. And I also made a handout on this as well. You might want to just watch the video. It's probably the quickest way to learn how to do the graphing. And then you kind of just have to play with it a little bit. Okay, so the second table is, again, another set of data. And for this set, we're going to assume it's some object that you're dropping near the Earth's surface, right? So if you hold, a piece of chalk and you release it, it's going to accelerate down. And we want to graph position versus time again. So here's your data for the time. Actually, it's the same as before, 0.0, 0.1, all the way up through 0.9. And then these are the position values in centimeters. Okay, so question 2 is plot a graph of the vertical position versus time. So again, time will be X, position will be Y. So be careful with that, X, Y. And it says, based on the shape of your graph and the fact that the data was generated by this function, so I made up this data using this function, y equals 4.9 t squared. Like, what kind of a relationship is it when I have a t squared? If this were just y equals 4.9 t, that would be linear. But what does t squared mean? Okay. Once you figure that out, you want to perform the fit. And just like with the other graph, you can check both of them against my graphs that I did down here. Now, I didn't use the same software, so it's going to look a little bit different, but it should have exactly the same shape, right? Don't forget when you do your graphs to include the labels with the units and the title. Again, we can just call this position versus time, right? Y versus X, and then the line of best fit or curve of best fit. In this case, it is a line. In the second one, you should find that it's going to look like a parabola, right? So it should be a quadratic fit. We'll give you that parabolic fit. Okay, now part B. So this is the part that Physics 206, Sports Physics Lab, does not have to worry about. But Physics 207 and Physics 212, you do definitely want to do this part, part B. So here's where we're going to investigate the relationship between the period and length of a simple pendulum. So you want to go to that simulation that I used, the PHET physics simulation. By the way, they have a bunch of really good simulations, and we're going to use many of them throughout the semester. Some labs, there's not one for every particular lab that we do, but many of the labs, there's some type of simulation that we can look at so you guys can collect some data. Okay, so actually let me go to that right now and I will show you how to collect the data. Here's your table. Basically, we want the time for 5 oscillations for each of these lengths of the pendulum. Okay, so 0 is done for you, right? When the length is 0, the time is 0. That means the period is 0. Period squared is also going to be 0. But I want to get the time for 5 complete oscillations when the length of the pendulum is 10 centimeters and 20, 30, 40, 50. So let me go to that simulation and show you guys how to do this. Okay, so we go to the simulation, click on play to start it. Click on the intro, that'll be fine. We don't need the ruler, so I'll get rid of the ruler. I'm gonna include the stopwatch. I'm gonna move it so that it's near the pause button here so I can control both of them at the same time. And then what you wanna do is you wanna set the length of this pendulum to be 10 centimeters to start. So that's that first bar up here. I can drag this to the point 1. I'm going to hit pause. And then I can set the angle by dragging it to -20 degrees. So you're right there. And then I'm going to hit start on the timer. Now remember, I want the time for 5 oscillations. So when it starts here, when it goes to the other side and back, that will be 1 oscillation. So it'll be 1, 2, 3, 4, 5. And I'll hit stop on the stopwatch. So if I hit the play button, it'll automatically start the timer, and then I just need to hit the stop button. Okay, so play, 1, 2, 3, 4, 5, stop. So 3.35 seconds would be the time for 5 oscillations when the length of the pendulum was 0.1 meters or 10 centimeters. Okay, then to do the next one, I'll pause this again. I'll reset the stopwatch. I'll change the length, so you need to go to 0.2 now. Go back to -20. Hit play on the stopwatch first, right? And now hit play button, the original play button or the general play button. It'll start it. 1, 2, 3, 4, 5, stop. So 4.64 would be the time for 5 oscillations when the length is 0.2 meters. And then I go to 0.3, 0.4, and 0.5. You want to do it for each of those different lengths. Okay, so now that you have those 5 times, you can fill in this table here. The next column is the period of that pendulum, right, in seconds. So if I know the period squared, or sorry, if I know the period for the time for 5 oscillations, how do I find the period, which remember is the time for 1 oscillation? So I would just take this value and divide by 5, right? So if I do this value divided by 5, that'll be the period for 10 centimeters. If I do the second value divided by 5, that'll be the period for 20 centimeters, and so on. And then finally, to get the last column, once I know the periods, just square these values on your calculator, right? Multiply them by itself, basically. So you're squaring these values to get period squared. Now, for all of these, I want you guys to make sure you round everything to 2 decimal places, right? So just round all these values to 2 decimal places. Okay, question 3. Another graph. We want to graph period versus length. That means the length is the x variable. So you might want to just make a little x here to remind yourself that's x. And the period will be the y. Okay, so period is y. So period versus length. Length is x, period is y. Make sure you include the 0.00. It's in the table here, and it's an important point, so we'll include it. And then here, this is the one that's a little tricky, so I'm going to actually show you guys this one. Remember, this ends up being like a square root function when we do period versus length. So what kind of fit is that? So let me go to the Pascal capstone and show you guys how to do this part. I'll show you something similar. Okay, so this is the startup screen for Pascal capstone. I'm gonna go to classic templates. Remember, there's another video showing you how to use the software. Just gonna show you that one graph that's a little tricky. We always want to use this left icon, upper left icon here where it has a table in the graph, so I'll click that one. Now, for the first data, it's going to be the length, right? The x value is going to be the length. So I'll go to select measurement, create new, user to enter data, and I'll type in length. And then I'll hit tab or enter and then do cm for centimeters. Then for the second column, select measurement, create new, user enter data. It's going to be the period, hit tab, and I'll do S for seconds. Okay. So then you guys will put in your data. I'm going to make up some data. Let's say my lengths are 0, 1, 4, 16, 25. I'm just making up some reasonable data that will give me, oh, you know, I forgot 9 here. Let me do 9 as well. 9, 16, 25. And then say 0, 1, maybe 2.1, 2.9, say 3.9, 5.1. I just want to make up some data that will look like a square root function, right? Like a sideways parabola. So then to plot this, I go to the x-axis, select measurement, and I can choose what I want as my x measurement. So in this case, I want length, right? And then for the y, select it, I want period. Let me put a title. So I'll just call this period versus length, right? Y versus X is fine. Remember, we don't want these line segment connections. So to get rid of them, you hover over one of the data points, right click it, and then uncheck show connecting lines. By the way, I think if you have a Mac, you have to do Control right click to do that. Okay, now, so here, it may not be obvious like what curve fit to use. Remember, the fits are this menu right here. If we click on the arrow to pull down the menu, it turns out if we do a power fit, that will work fine as long as the power, or the n here, ends up being a half, right? Because a half means a square root. So I'll do a power fit. And notice that it doesn't really do a great fit. Let me recenter this. Doesn't do a great fit at first, but we can fix this. If you click on the information of the power fit, you can go to the curve fit editor right here, or I can just click on it. It brings it up over here on the side, on the sidebar. So I'll just click curve fit editor. And I want to do several things because I want this to give me a better fit to the data. So I know that this, I don't want it to be shifted left or right. So the X naught here, I want to be 0, and I'm going to lock it at 0 to make sure it stays at 0. The B would be like a vertical shift. You guys remember from pre-calculus or college algebra, like a vertical shift of the graph. I want that to be 0 as well, so I'm going to lock that at 0. And then the N, that's where I want it to be a half. So I'll just do 0.5 and lock it at 0.5. The A is going to be how much it expands or contracts. And that, I think 0 will be okay if I just leave it at 0. But the other ones, I want 0, 0.5, and I want to lock those 3. Now, if I do update fit, hopefully it gives me a better fit. Actually, yeah, that's much better. So now it actually looks like a sideways parabola. Great. So now I can get rid of that screen. So I have my title. I have labels with units. I have my data with a nice fit through the data point. So that looks like a great graph of period versus length. So now to save this, let me just remind you, remember you click on the graph, go over to the border, right? So it's highlighted, right click, and then go to copy display, and then you can paste it wherever you want. So typically I paste things into Word documents. I know some students like to use like Google Docs, like especially if you're doing this in lab groups. This first lab, you're gonna work individually, but all the other labs, you'll be working typically in groups of 3. So you may wanna just share everything on Google Docs, that's fine. So you just paste it into whatever you're gonna use to submit your lab report, okay? All right, let's go back to the handout. Okay, so now we've answered question 3, right? We've done that graph. Just make sure you answer this part. What is the shape of your graph? Question 4 was plot or graph period squared versus length. So if you look in the table here, length again will be X, period squared will be Y. So this last column will be your Y. And remember, that one should be linear, right? So you want to do a linear fit when you do that period squared versus length. And when you do that linear fit, it'll give you the slope, and you're going to need that slope value to answer the last question. Because the question 5 is write an equation that gives the period as a function of the length. So remember, we sort of derived that earlier in this video lecture. It's going to be t equals the square root of m times the square root of L. But now you have your slope from question 4, from the graph of question 4. So now you can plug in your m and you have an equation. You're going to get t equals some value. It'll probably be around 0.2 times square root of L. Okay, so this last part is just to remind you. So for the first lab, this lab 0, I want everyone to submit a lab report, right? In the future, every other lab, we're going to work in groups, typically groups of 3. But for the first lab, I want to make sure everyone knows how to do the submission and everyone knows how to do the graphing. So I want everyone to submit this lab 0. How should you do the lab report? Well, you want to make sure you have a cover page with the name of the lab. You can just say lab 0 graphing, and also your name. So make sure your name is underneath the title. Make sure you include all the tables of data. So anytime I have like tables in my handout, you want to make sure you copy and paste those into your lab report, and they should be filled in. Some of them, of course, are already filled in based on this first lab, but these you want to fill them in. So just go to my Word document on Brightspace and you can copy and paste anything in. And then any graphs that you have, remember you want to copy those and paste those as well into your lab report. Make sure you answer all the questions, right? Some of them, you know, require a sentence or 2, so make sure you do that. And then when you submit them, they're going to be submitted through Brightspace. And when you go to your Brightspace class, there's an activities tab, and underneath that is assignment. So I'll have like an assignment 0, and you can just upload your lab report. Now make sure that you upload your report as a PDF. So convert everything to PDF. It's just much easier for me to grade everything when it's a PDF. So make sure it's a PDF format, okay? The first lab, this lab 0, I'm just gonna grade everyone pass fail just to make sure you did it, right? And then you have some practice with graphing and you know how to submit lab reports. And then later on throughout the semester, when you do your group lab reports, those will be graded on a scale from 0 to 10. And if you do everything I ask, if you show me all the calculations, this first one really didn't have any calculations, but later ones will have a lot of calculations, then you're going to get 10 or very close to 10, right? So you just have to make sure you do everything that's asked in the lab handouts. If you answer all the questions, you're going to do very well in these lab reports. All right, so that's it for lab 0, and great, good luck.